This is the second lecture in the Toolbox Basics course, and here I'll show you how to install the Toolbox on your own machine and run your first model. My name's Stuart Heitman, and I'm recording this from home because we just happen to be in the midst of a COVID-19 lockdown. Alright, so I assume you've been to the bdtoolbox.org website and downloaded the latest version of the Toolbox. I have mine here on the desktop. I'm using version 2021A. I've also got the sample chapter of the handbook, which includes the installation instructions. Now, installation is actually very easy. All you need to do is unzip that installation folder and add some paths to it in MATLAB. So let's just go right ahead and do that. I will unzip this onto my desktop. You can install it anywhere you please. Let's have a quick look inside to orient ourselves. Now the root node of this installation directory contains all the BD Toolbox functions. They're all prefixed with BD for Brain Dynamics. The one that you'll be interested in mostly is BD GUI. That's the Brain Dynamics Graphic User Interface. It's also worth checking the release notes while you're there, just to make sure that you have the right version of MATLAB. In this case, I need MATLAB 2020A or newer. And I'm using MATLAB 2021A, so that's okay. The other directory of interest in the installation folder is this models subdirectory. That's where the example models are kept. These are listed in the handbook also, so you can get a quick summary of what those models are. Today I want to show you the LinearODE model because that is the simplest model there is in the Toolbox, and so that's always a good place to start. And there it is right there. So let's go ahead and add the paths to that Toolbox and run that LinearODE model. Add path, BD Toolbox 2021A, add path, BD Toolbox 2021A models, and that's all we need to do. Now I can run the help function on that LinearODE model just to see what it does. And it tells me that the LinearODE model implements this system of ordinary differential equations. There are two state variables, x and y, and four parameters, a, b, c, d. Perhaps more importantly, it tells us how to run that, how to use that script to construct the model, and then how to pass the model to the Brain Dynamics Toolbox GUI. And so this two-stage process is typical for all models in the Brain Dynamics Toolbox. There is a model-specific script that constructs the model and returns it in a special MATLAB structure called a system structure, and then we pass that system structure to the Brain Dynamics GUI that actually runs the model and performs a simulation. So let's try that. Sys equals a LinearODE. There we can see the MATLAB structure. It's just a MATLAB structure. There's nothing special about it except that the fields within it obey certain conventions required by the Toolbox GUI, and we can run that GUI with BD GUI sys, and this will start the graphic user interface with that LinearODE model. So it does take a little while for MATLAB graphics to get up and running, so we just sit patiently for a couple of seconds while it gets itself sorted out. We'll know it's finished when that cursor wheel stops spinning. So there we have it. If you've gotten this far, then you know you have a properly installed Toolbox installation. Alright, so the LinearODE model, let's go around the interface and familiarize ourselves with it. Here we have the display panels. We can click on different panels to get different views of the simulation. Notice that each time that we click on a panel that this menu here changes. So you have a specific menu for each panel. And if you want to add a new panel, you can select one from the new panel drop down menu. So I could select, for example, the bifurcation panel, and that will construct a new bifurcation panel here. And if I don't want to keep it, I can select the bifurcation menu and close that panel. So on the right we have the parameters of this particular model. Remember, there's A, B, C, and D are the 4 parameters, and the initial conditions. So we have initial conditions for X and Y, and we can see this in our time portrait. This plots the time course of X here in the upper plot and the time course of Y in the lower plot. And there are only 2 variables in this model, but if we want to, we can choose what we're plotting in each of the 2 panels. So this selector here controls the bottom panel, and this selector here controls the upper panel. Now, whenever we change any of these parameters in our system, I'm just clicking here to change parameter B. You'll see that the solution is automatically recomputed and replotted after each change. And not just in the panel I'm viewing, but in all panels simultaneously. So we'll see the phase portrait changing as I change parameter B, and the time portrait changing. And the same goes for the initial conditions X and Y. So here I can change the initial condition of X to 0, say, and we'll see it's changed right there. That pentagram represents the initial condition. If I can change it to 1, there we are up there. I can clear the axis to get rid of those labels. Now, here you might notice that we can't see all of the trajectory of the Y state variable. Now, if we can change that manually by unchecking this box on the initial conditions, and this reveals these lower and upper limits for each of the controls. So these lower and upper limits control 2 things. They control the lower and upper limits of the slider, and they also control the lower and upper limits of all the display panels. So in this case, the Y is plotting between -1 and 1. Let's say we want it to plot from -2 to 2. We just change those parameters in there, and we can see the plot axis has automatically changed. And it also changes in the other displays as well. So here Y is now from -2 to 2. We could do that automatically. Many panels support this calibrate option. So the phase portrait has one, the time portrait has one. It depends on the panel that you're using. But the calibrate function essentially adjusts these lower and upper plot limits of the variables that you're observing currently according to best fit that data. So if we just go time portrait calibrate, we'll see the upper and lower plot limits now fit that data perfectly, and we can see those values here. And those values are also affect the sliders. So if I slide my X value down to the minimum, there it is there at 0.56 or whatever it is, 0.58, up to the maximum of 1. Alright, so that applies to the parameters as much as it applies to the initial conditions. It also applies to the time domain. So I haven't talked about this yet. The time domain section down here describes the or defines the time domain. It's the start and the end simulation. Start and end times of the simulation, I'm trying to say. Here, the simulation starts at time 0 and ends at time 20. We could change this to go from 0 to 2, or 0 to 200. And you'll see that the simulation is automatically updated. And as usual, it's also changed in the phase portrait and the solver plots. The solver plot's interesting. It tells you the step sizes taken by the solver. In this case, I'm using the ODE 45 solver. So this bottom toolbar here tells us or allows us to control the solver that we use. I could choose the ODE 23 solver, for example, and it would use a different set of time steps because it uses a different algorithm. Again, these are a bit hard to see because the plots are so low, so we can go solver, calibrate, and recalibrate those plots. And here we see ODE 23 settles into time steps of about 0.8 milliseconds. If we switch back to ODE 45, it chooses time steps of about one second, or whatever the time scale is for this particular model. I'd also mention lastly that the time domain has this time slider. This allows you to move backwards and forwards in your simulation to segregate your simulation into two parts. One, the light grey represents the transient part, and the black part represents the steady state solution. And that's quite useful in phase portraits when you want to look at limit cycles, for example. We don't have one here, but I can drag my time slider right back to the beginning and move it slowly through, and you can see how that solution converges to the point 0, 0, where the null lines happen to cross. Let's look at that in the time portrait. Moving back to the beginning of the simulation. Let's make it a shorter simulation so it's simpler. 20, let's go 10, 0 to 10. Alright, move that slider forward from 0 up to, let's say, 8. I can put in 8 here. And if I do the same here, I can see the beginning, moving my slider through time. I can see how that solution converges to the fixed point. And in this case, I can hide the transients, suppress them from being plotted, and just see the fixed point there. I can do the same in the time portrait. If I don't want to see all this transient stuff, I can just go time portrait, turn off the transients, and we see the plot beginning at 7.659. Let's make it 8. From 8 right through to 10. Same there. Put the transients back, and we can see where our simulation began. We can halt the solver if we want to change a few parameters at once. And when we release the solver, it recomputes. If we want to force it to run, we can just click it once on the run button, and that can be useful if we want to evolve the solution. And this evolve button here does exactly that. So if I enable the evolve button, what happens is at the end of each simulation, the final stage of the solution is reused as the initial conditions in the next run. So if I evolve this system and go run, 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 you'll see that it's just evolving down to that fixed point right there. I can choose a random initial condition, and I can choose a very short run time. Let's run it for 0.1 second. Let's run it for even shorter, 0.001. Okay, now if I evolve that, you'll see that converging, Don't know what happened there. Let's run it some more. Okay, I think I used the wrong time step. 0.01, 0.1, that's better, we can see that. So each time I evolve that, you'll see the final stage, which is in black, becomes the new initial stage, which is the yellow star. Okay, so the final conditions of what the previous simulation become the initial conditions of the next one. All right, run, 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 run. I just hold run down and you'll see it converging to that fixed point. Now I can put the graphic hold on here if you like, and we can see how that evolves in time. Okay, look, and I think that's a good place to stop. That's a quick introduction to the main features. We'll go through more features as we progress with the subsequent lectures, but for now I'll stop here and let you have a chance to install that zip file and add those paths and run that linear model to get familiar with the graphical user interface.